Good morning, lovely 13s. Right, buddies. Today's a very exciting lesson because we are going to be doing something called integrating factors with differential equations. And actually, I would say, having finished all of the rest of your guys' course, I think this is definitely far and away the very hardest thing that we have to do together today. So I'm going to break it up into two lessons, essentially. So I'm going to probably do loads of long video today, and you should be trying to be like one step ahead of me a little bit, and I'll try to give you cues when you should be doing that, and try a few questions today. But then the very next lesson, I'm going to give you tons and tons and tons of time to practice, because I think that's what it's going to take. Okay, cool beans. Title is Integrating Factors. Now, to start with, you guys have been solving differential equations, but only in the type where you could do separation of variables. Now, I've just written it generally here for you to see. That's what that is. Separation of variable works like this. If you have a function of x times by a function of y, you were able just to use division and multiplication to get the x's with the dx's and the y's with the dy's. So what you've done is you've made the variable match to their you've made the functions of x match with their matching derivative, and the same with y, and then you were able to integrate both sides. Now here's the thing. Most functions aren't actually written in this format, and so we have to have kind of several strategies depending on what type of differential equation that we have. So what I'm going to do with you today is a solution that works for all first-order linear differential equations. Okay? Now, I think you will have to know what those words mean, but I'm just going to show you this really quick. Any first-order linear differential equation is written in this format here. So you've got your derivative, dy dx, plus py equals q. But it's really important to note that p and q are not just like letters like a and b or c and k like we usually use for constants. They're not constants, they're actually functions of x in their own right. So for instance, p might be something like negative x squared, and q could be something like e to the 5x. Cool beans? These are all functions of x. So here's what I mean by first order. Now, a function is first order if the highest power of the derivative is 1, which means that there's a first derivative in it, which means there's a dy dx in it, but not a d squared y by dx squared or a d cubed y by dx cubed. The highest derivative is order 1. So this is in matching with this general form does match up with the first order. The highest power is dy dx, which is of order 1. Now it's linear if the highest power of y is 1, okay? So the thing that you're differentiating with respect to has to have its highest power as 1. So this is true because y is just to the power of 1. Now, x can be any power at all. The dependent variable can have any power at all. We're differentiating y with respect to x, so it's the y that's got this extra condition of having to have its highest power of order 1. So I just had a real quick question for you there. Is this a first order linear differential equation? Oh my god, it's a mouthful, isn't it? Is that a first order linear differential equation? If you said, yes it is, you're absolutely right. It is first of all going to be first order because of this. So red tick for the red criteria there. It's first order because its highest derivative is dy dx, which is a power 1, so it's first order. The next thing, linear, I better find purple. Is it linear? Well, yes, because the highest power of y is also 1. Okie doke, my buddies, the highest power of y is also 1, so it is linear as well. Now, the follow-up question, what are p and q? Well, this isn't too bad, I don't think, anymore. To get p and q, here's what you gotta do. You're just gonna rewrite this majestic beast to match up with this one here. So dy dx is gonna be on the left-hand side with the py with it. So here we go. Already, we've got dy dx on the correct side, so dy dx. And what we're going to do is whatever's touching the y is going to go over with it. So minus x squared y, and then the singular function of x is on this side, x squared. That's put it in the same format. So my buddies, if you look at it, what's p equal to? Well, p is equal to negative x squared. Bish, bash, bosh. p equals negative x squared. And what does q equal? Well, q is a function of x on its own, so in this instance, q equals x squared. Cool. So I hope you get your head around it. It's just funny terminology, and it's about getting it in the correct form. So here we go. What I'm going to get us to do now, and I've put notes for me to remind you, because I'm going to try to build to something with this. This is going to be a motivating example if I pull it off, so fingers crossed for me and for you. So here we go. It says find the general solution to this differential equation. Now, I've not actually given you the method yet to do this, so what we're going to have to do is we're going to have a little bit of a messing around with it, okay, my buddies? So that's the first step that we're going to do, is have a bit of a messing around with it. Now, what I'm going to show you is, yeah, I'm going to give you a bit of a step here. Okay, first things first, we want it to be, actually we don't want it to be in that format, no, because we're not actually doing it properly yet. Okay, here's what I'm going to suggest. What's making it awkward? This is not the usual way of approaching these questions, and you'll see that in a minute, but we're still going to try to solve it. We're going to try to get the general solution. So we're going to get rid of the dy dx and so on like that. Now, to start with, I hope if you've had a little look at it, you have a dy dx there, and you have a 1 over x with a y, plus on this side there's an x squared on its own. Can you see that separation of variables isn't going to work here? Because it's really mucky, and I can't really, the subtraction, if I were to move that to the other side, is going to become a problem. I'm going to have a difficult time factorizing because I'm going to end up with fractions if I factorize it as well, and a fraction is going to end up being times onto the derivative, and it's going to break everything. So separation of variables isn't going to work. So here's what we can do. Let's try to tidy it. Why don't you guys do this too? Start by just timesing both sides by x, okay? Now that's what we're going to do. We're going to just times both sides by x. And you're going to get this then. You're going to get x dy dx. Dx, then it's going to be plus, just y, it's going to be plus y equals x cubed. I guess I didn't need that one to be purple. I'll show you that later. I'll show you that part later. I'm going to make it black again. Okay, so that's what you're going to get. Now, here's the thing. I'm going to tell you guys something amazing here, and it's going to blow your mind, and it's going to be something that's incredibly, incredibly hard to spot, but it won't be really soon. As soon as we actually get a method down here, it's not going to be too difficult to solve. Now, there's something weird about this left-hand side written the way that it is. It's quite contrived, I'll give it that, but it is something that you can potentially spot. We have x times by the derivative of y with respect to x, and then you have y on its own. I'll give you another hint. I could have dx dx with y. Well, my buddies, I don't think you're going to spot it. Well, maybe you might spot it. Who knows? Maybe you did spot it. I wonder if anyone spotted it. Here's the thing. This is this, my buddies. The red is that. Now, what I'm basically just said there, and this is like so hard to spot, and that's why we've got to have a strategy here too. What I'm saying is, what's in black here is actually the derivative of x times y when you use implicit differentiation, which is an absolute nightmare. So, let's just confirm it, okay? If I said that so it's easier to start with the red and go back to the black. But here's what I spot. Oh, anyway, the way I did it is that there's a dy dx, and that was a big flag to me in touching the x and the y. But again, you don't have to be able to spot this because there's a shortcut. Now, here we go. Let's just confirm it. If you were to take the derivative, let's just do it over here. I'm just going to do a little aside over here. If you were to actually differentiate xy, it's going to be a product rule, isn't it? So you differentiate the first, you differentiate x, and that gives you 1 times by the second, which gives you y, plus leave the first, x, and then you differentiate the second with respect to to x, and you get dy dx, which is actually just x dy dx plus y. So actually, which matches up, of course, then with the black above. So actually, buddies, it equals x cubed, just like that. So we just have the right-hand side written down, but the left-hand side, I've written it as a derivative instead of, I've written it as a derivative, my lovelies, rather than as a mix of things. It's now just the derivative of two things together. I found that it was a product rule. Now there's some awkward words that I need to get out here, my buddies, because it's going to become really important in a sec. This thing here that we times by up here, remember when we times both sides by x, we times everything by x? This, my buddies, is called an integrating factor. Okay, something you times both sides by is an integrating factor. And this, what I've highlighted in red there, my buddies, this is called a perfect derivative. Okay, now a perfect derivative is just any answer to a product rule, okay? So it is like expressed as a product rule, okay? It's a perfect derivative if it can be expressed as a derivative of a product, that's the formal definition, as the derivative of a product. Okay, now I know it feels like a handful, and it will get harder from here, but then it gets easier. So don't worry, buddies, we got this thing. Okay, so that's what you got then. So hopefully, I know it'd be impossible to spot pretty much, but you agree now that this does turn into red, right? Okay, well now we're in a position to solve, because look, buddies, as I've got a derivative up here, this is like differentiate this, that's what that means. We can integrate both sides now. So if you were to go ahead and integrate both sides, well, what you're going to find is this. The left side just becomes xy because you're going to integrate a derivative. It just gets rid of it. And on this side, when you integrate it, it's going to become x to the 4 over 4 plus an integration constant, right? From both sides, actually, we combine it together as 1. Which means, here we go, buddies, y is simply going to be equal to, divide both sides by x here, and you're going to get y equals x cubed over 4 plus c over x, and bang, there's your general solution. Now, I hope that you kind of see that the idea of this was that you kind of see what happened. We times an x by both sides to kind of force ourselves into a position where a perfect derivative existed, okay? By timesing by the purple x, we ended up in this scenario here, where the left-hand side made a perfect derivative. Since the left-hand side was a perfect derivative, I wrote it as gosh, what's the word I'm looking for? A differential, I think, of a product. So in other words, I was able to take the answer to a product rule and instead write it as a product rule. Cool? Because once you do that, you can integrate both sides as normal. Bish bash bosh, answer. Okay, now ready for your nightmare, my buddies. I'm gonna prove it because when I've not done differential equations all the way since university, and I found it when I did this proof kind of on my own, trying to be ahead of the book, and the book wasn't super at it. I found the proof quite useful, and so I think I'm gonna do it with you. It helped me, and I'm gonna think that it would help you too. So here we go. I'm gonna show you something cool. Here it is again in general form, okay? dy dx plus py equals q. This is one of them in general form. So you're going to have a derivative plus a function of x times by y equaling another function of x. Now, remember how we times both sides by x in the first step? It just got lucky that we times by x. If this was a harder function, it wouldn't be x that we times by. And it could actually be something quite tricky. Like you could have something, I don't know, like cos of x times by the y or something. And then what the devil do you times by there? Like how do you fix it then? Well, the thing you times by is actually this. The integrating factor is the e to the power of the integral of p dx. Now, for our proof, I'm going to call it r, but usually you call it f of x, okay? This is the integrating factor. You should jot that in your book because this is going to be, I know it looks hard, but this is going to be your best friend in the whole world, okay? These are the integrating factor. Grating factor. Okay, so essentially, no matter what the question says, if you just times both sides by e to the integral of p dx, where p is the thing touching y, then you're going to make it work every time, and there's a sick shortcut. But I'm going to prove it. So buckle your seatbelts, and I've pre-written it because I was worried it would take me like 3/4 of an hour to do this proof alone, so I've pre-written it for you. Okay, here's what you're going to do, my buddies. Start off with dy dx plus py equals q. So get that jotted into your book. Cool beans? And here's what you can do. we're going to multiply through by the integrating factor. I've called it r in this case, so we're using the one on the right-hand side, but in every single question after this, I'm calling it f of x, because I remember learning it that way. And actually, I think your textbook does it that way too. I just think that the MEI resources don't. So you're going to times everything through by an integrating factor r. Now, what that's doing again, my buddies, is that's preparing the question like this. It's preparing it so that the left-hand side will become a perfect square. I'm going to prove to you, or not a perfect square, perfect derivative. Cool. So r in front of there, rpy, qr. Boosh. Next thing, my buddies, we need the left-hand side, this. The goal of this entire process is to turn the left-hand side into a perfect derivative, because this is a perfect derivative again. Remember how the xy in the red there? We wanted that because when it was written as a potential product rule, then we were able to integrate both sides, and that sorted it. So here we go. We're going to do that on this side. Now, if it's going to be a perfect derivative, it's going to be in the form ry. Okay? Now, it's ry because in our previous one, remember how we had x dy dx, or we had x dy dx plus y was the left-hand side of the previous one? See? X dy dx plus y was the left-hand side of the previous one. Well, the thing that we ended up with was xy. So I'm just copying in position that. Okay? So xy, it's going to be ry in our case. Cool beans, buddies? Right then. So here's what you're going to do next, my buddies. I think I've got it recopied, so here we go. It's written like that. So product rule it, buddies. See if you can get that with product rule. It's implicit differentiation. So first step first, you're going to differentiate the r. So you're going to get dr dx. Then you're going to leave the y. dr dx y. Then you're going to go plus. Then you're going to leave the r dy dx. And that's how you, oops, oh, drat, clicking on something underneath. And that's how you wind up with that. Can you see that that's product rule? I hope you can. I hope that you can see that that's product rule. Now, here's the thing. That's to replace the left-hand side, right? Remember how our goal is to swap out the left-hand side. This. We want rid of this part here. Not equals QR, but this part here. We want rid of that. We want it written as a perfect derivative. Which means that this format here, which can be expressed like that, has to actually equal what the left-hand side actually equals. Cool? At which stage you can equate coefficients. So if you see, my lovelies, the constant one, or the ones with dy dx's, you're going to just get this, the red underline equals the red underline, so no information new there. But in terms of y, you're going to get a new equation. You're going to get that dr dx is just going to have to equal rp. So equating on y, like what you would for partial fractions and stuff like that, and there's what you get. Well, now this is cool, because now you can go about your regular separation of variables, because we just have an r and a p and a dx and a dr, so we're sorted. You can do your regular separation of variables and get all the way to the answer. Boom, just like that. So 1 over r dr, p dx. Integration sign on both sides, which means on the left-hand side, what are you going to get? Well, ln of r. And on the right-hand side, what are you going to get? Oh, if you said px, you're not quite right, because what do you get when you integrate that? P is not actually a constant, so it's not going to be px. It's going to just stay as it is. Do you follow? Because p is like a function, okay? We can't integrate the function if we do not know what it is. P is just a function of x. But anyway, you can rewrite it, and there you go. Happy days. This is why the thing that you times both sides by, going right back to the start, we times both sides by x here, the thing that you times both sides by, you can always determine by using this as a little formula. It's e to the power of the integral of p dx, and that is that. Cool. How does it solve generally? Well, let's see. Here's the general form again, so I'm still proving, my buddies, but we'll be done proving soon, and you're going to see that it works. It works cool. Okay, there it is in general form. I'm keeping it in complete generality so you can see how it works. Now, the integrating factor, r is what we just called it, I think out of convenience and When I did it, it was very complicated. When I had f of x there and ended up erasing it all, so I chose to go with r. I thought that was a good shout, but now that we're done that hard part, we can go back to f of x's. There's our integrating factor, okay? So we're going to be timesing both sides by our integrating factor as the first step. Okie doke. So let's do it. Times both sides by the integrating factor. Well, you're going to get this. I've got it just algebraically first, or I've got it in function notation first. F of x dy dx, f of x py, f of x q. Cool? But we know that the integrating factor is the integral of p dx. Or e to the power of the integral of p dx, I should say. So swap them all out for that. Now, here's the cool thing, buddies, that you may not even believe me. Well, actually, we're not quite at the cool thing yet. But yeah, we're rewriting it just like that. So I've just got the p written first as it is a constant at the end of the day. So, or it's a function of x. I want to get it. I'm trying to make the form exactly match the form above. Yeah, buddies, that's what I'm doing. So the form is beautiful now. And here we go. This left-hand side is a perfect derivative. Okay, which means that it's going to be this. It's going to be e with y, the two things that you're dealing with, yeah? Now, it's not clear to see that. Like, we relied on that fact to get this, okay? So we actually have used this fact already that it is a perfect derivative, but I still think it's not all the way clear to see. So how do we know that this is a perfect derivative? Well, we know because if we actually carry out this differentiation with product rule, we're going to see that it works, okay? So here we go, product rule. We're going to differentiate the red. Okay, if you differentiate e to the power of p dx, this is chain rule, okay, to start with. So it's e to the p dx is going to is going to differentiate to e to the p dx. But then, my buddies, you have to use chain rule. And what happens when you differentiate the integral of p dx? Well, differentiate and integral are opposite, so just p. Cool? Y's chillin'. So differentiate the first, leave the second. Cool? And that's why y is in blue, it's the second. Now in the second thing, you go plus, leave the first, integral of p dx, and then differentiate the second with respect to x. You're going to get dy dx, which, boom, matches up with that. So there we go, my buddies. Now, this is it completely in general terms. We've just shown that it works. You know that the integrating factor is e to the power of the integral of p dx. And you know this, you can replace whatever the awkward, ugly left-hand side is with the integration factor, or the integrating factor, which is e to the p dx, simply times by y. Cool? It's horrible. It's tricky, isn't it, to start with? But guess what, my lovelies? You're going to be absolutely beastly good at this now, and it's going to allow us to actually do a real question. So just jot it down again what the general form was, and let's try this question now. So jot that question down, and I will do it with you. It's not too bad, actually. It's an okay one. Cool. So here we go. To start with, this question's already in the nice format, okay? And this is actually using it for real, so we're actually just going to start busting through our stuff now. So to start with, it's dy dx is equal to p, py equals q. So there's where we are. Which means, my lovelies, what's p? Well, that's p. Cool. What's q? Well, this whole thing is q, right? P is the function of x that touches y, and q is the function of x that's on its own. So step one, buddies, is we want to times both sides by the integrating factor, but before we can do that, we have to actually get the integrating factor. So we're not necessarily going to times both sides by x like we did last time. Like, maybe that's the thing that makes the perfect square on the left-hand side, but maybe it's something different after times by. So here we go. To start with, let's get the integrating factor. Okay. Now, if you're after the integrating factor, remember our rule, my lovelies. The integrating factor is given variable f of x, and it is going to be the e to the integral of p dx. Okay? Well, let's start popping our numbers in then. So f of x equals e to the integral, and p is 1 over x dx. Cool. So f of x equals e to the, okay, and the integral of 1 over x is ln x, you got it, ln x, brilliant, like that, and that's what we've got. Now e to the ln of x is simply just going to be x. Okie doke. So f of x, we're just going to get here as x. Bish bash bosh, that's your integrating factor, okay, for this question. So it was x in the end of the day, but yeah, anyway, that's what we got as our integrating factor. Now let's keep going. So now we're going to actually solve. So your first step then, buddies, let's get a different color. I don't want red, it's too harsh. Okay, let's go with this. Now we're going to multiply through, okay? So, so here we go. So, do I want to do it with steps? Do I want to do it with steps? No, I don't. So multiply through, multiply through. We're going to skip a step. Multiply through. Okay, which means, here we go. We're going to get x dy dx, multiplying through the original, plus y, equals 4x cubed. Oh, I ditched the integration constant here because there's going to be an integration constant later on, which will take care of it as well. So just if you're wondering why I ditched the integration constant. Okay, now the second side here is guaranteed, my lovelies, and here I'm going to do an extra step actually. This second side here is guaranteed to be a perfect square, my lovely, or it's not perfect square, a perfect derivative. So yeah, let's rock on. Let's do it. It's guaranteed to be a perfect derivative, and we know now from this part here that that perfect derivative from this part here is simply going to be the integrating factor times by the y, and so that's what we're going to get. So on this side here, and here's the extra step, that means that this part here is definitely going to be turned into, I don't know, I drew an integral sign. It's going to be d dx, and then it's going to be the integrating factor, which I'm just going to call f of x for now. This is the extra step I don't need to show, times y. So there, did you see that in general? Can you see how I just nailed that generally, my buddies? Okay, sweet. And then on that side there, it's going to equal 4x cubed. But actually, my buddies, in our case, f of x is actually x. So it's d dx of xy equals 4x cubed. 4x cubed. And there we go. So the reason I wanted to show that is, can you see it's just the integrating factor times by y if you follow this procedure, which is amazing. Okay, now here's what we're going to do next. We're going to just integrate both sides because we want to get rid of the d dx, and we're going to be left with this. We're going to be left with xy, we'll do it in blue, xy equals, raise the power by 1, 4x to the power of 4 over 4. Which I hope, I'm just going to write x, no I'm not, 4x to the 4 over 4, raise the power by 1 divided by the new power, plus c. Cool beans, buddies. Let's make y the subject, and you've done it. So that means y equals, and we're going to be left with here, the 4's are going to clearly cancel, divide both sides by x, you're going to just be left with y equals x cubed plus c over x, and that's the general solution. So you solved it, buddies. The trick to solving all these questions is, number 1, find the integrating factor. Number 2, pop it in and watch the magic unfold. Terrible, terrible explanation, but yeah. Okay, so here's what I'd suggest, my lovelies. I would suggest that you guys do try this one on your own, I would say. It's not quite as simple as it looks. Okay, I'm going to copy and paste this, and then I'm going to say try it on your own. I think you should try this one on your own, but just note, my buddies, is this exactly in that format yet? Well, no, it isn't yet, is it? So what we're going to have to do is we're going to have to get dy dx on its own to begin with, aren't we? That is definitely the way forward. So, yeah, I'll do the first step, then I think you should pause. If you want to pause now and try to get ahead. It's almost the same as the last question, but yeah, if you want to pause, go for it. Okay, and I'm back. Here we go. So I'm going to divide both sides by x. So we're going to get dy dx. And this is just going to, not equals, dy dx plus, it's going to be 2 over x, leaving the y chilling because I want the y to be separate from the p. I want it to be really clear what p is. And that's going to equal 4 over x squared. Okay, and there's what we've got. This is p, this is q. Cool beans, buddies, P and Q. So P, Q. Okay, get the integrating factor. Get IF. Okay. Now, the integrating factor, of course, is f of x is equal to the integral. Oh, it's not. It's equal to e to the power of the integral. E to the integral of p dx, but p is 2 over x, so it's going to be 2 over x dx. Cool beans. Okay, I'm going to pull the 2 out in one step, so I'm going to be left with e to the power of, and this is going to be 2 ln x. Okay, I'm going to hit up the log rule on it, and I'm going to be left with e to the power of ln of x squared. The only reason I'm doing that is because I can see a simplification about to happen. I want the ln's and the e's and stuff to go away, which means our integrating factor in this majestic beast is x squared. Okay, sweet. Now here's what you're going to do, solve. Well, when we solve, we're going to go back into the original, so we're going to times everything by that integrating factor. So here we're going to get x squared dy dx, my buddies. Just having a little check here. I don't want to make any mistakes. I would be gutted if I did a mistake on you now. So yeah, definitely, yeah, I'm cool. This is good. Okay, so times everything by x squared dy dx. dy dx. This guy here, what we're going to be left with is, I'm going to abandon the colors as well, x squared dy dx, and then I'm just going to be left with 2x, I believe that will be x squared dy dx. I should just do it and stop chatting. I should just do it and stop chatting, that's what I should do. Plus 2xy equals, and timesing this by x squared, you're just going to be left with 4. Okay, now I know my trick as well, so I know that for sure this side is going to be defined to be a perfect derivative. So it's going to be d dx, and what we're going to get here is it's going to be our integrating factor times by y. So we're going to get our integrating factor times by y, so it's going to be x squared y, and that's just going to equal 4. So happy days, my lovelies. Should I have shown that middle step? Because it's always d dx. It's always going to be the integrating factor times by y, because that's what we did to make the integrating factor. Cool beans. Which means now we can integrate both sides. X squared y is going to equal 4x, but now we want the integration constant because we're going for an answer now, which means that y is just going to be equaling 4 over x plus c over x squared. And that's what you've got then, buddies, as your final answer. And I hope that that makes sense. It's tricky, but it's not too tricky. You just start feeling patterny yet. Because it'll feel patterny really soon. Cool. Right, buddies. Final one for today. How many minutes am I on? Oh my god, 30 minutes already. Okay. It is a long video, but again, remember, I'm giving you practice next lesson, okay? It's going to be largely practice. Okay. What I think you should do here is you should definitely pause. Now, this is a particular solution, so do exactly the same steps right to the very end, and then pop in y is 1 when x is 2, and then you'll be able to get c as well. I would strongly suggest right now you pause and you do it. I'm just going to cut and paste that again for your convenience, because you'll have it memorized shortly. But yeah, use that. Get it in the correct format first, integrating factor. Definitely pause. Don't watch me do this one. Go. Right, and here we go. Let's see how we've got on. So, to start with, I'm going to divide both sides by x squared, so I'm going to be left with dy dx plus, and this is going to be 1 over x times y, and on this side equals 2 over x cubed. That's right. Dividing both sides by x squared. Yep, definitely. Oh, my brain's melting a bit now, but yep, that's right. Okay, next thing, what we are going to do is we now know what P is, so there we go. That's P, and we know what Q is as well. And let's do it. Let's crush it. P, it's our last one. How exciting. Okay, so get the integrating factor. Get IF. Well, the IF then, buddies, f of x is going to be equal to e to the integral of p dx, p being 1 over x dx. dx, which means that it's going to be equal to e to the ln of x, which means it is just simply x as our integrating factor. Cool beans. Next step, times both sides by the integrating factor to construct a perfect derivative. So we're going to be left with x dy dx plus y, oh, it's the same ones that we've had a few times actually, equals 2 over x squared when you times both sides by x. Now you don't forget, my buddies, this is the cool part, d dx. It's just going to be f of x, the integrating factor. I'm going to cut to the chase though. The integrating factor is x times by y. So there you go, it's the integrating factor times by y. And on this side, I'm going to rewrite this as 2x to the minus 2 for a mysterious reason at the moment. Okay, next step, integrate both sides. X, y equals, now here we go. This is going to be 2x raised to the power to minus 1 divided by the new power of minus 1, which means that we are going to be left with xy equals negative 2 over x, which means if we want y to be the subject, oh, plus c, naughty, naughty, plus c, plus, I haven't divided yet, have I? Nope, plus c, okay, there we go, which means, my lovelies, y equals negative 2 over x plus c over x, plus c over x. So there we go, not playing games, we are absolutely flying. Now that, my lovelies, is our general solution to this majestic thing, and here we go. Divided by x. I made a mistake, didn't I? Oh dear. Where is it? I already had an x on the bottom. I see it. I was like, this doesn't look right. Why are they both over x even though this one had an x on the bottom? I smelt a mistake and I was right. This is x squared on the bottom because I needed to divide everything by x, so I missed the first one. Sorry, buddies. That, I'm pretty sure now, is the general solution. That is definitely right then. Okay, so to get particular then, all we got to do then is the particular solution, figure out what the bits and bobs are. We know that when x is 2, y is 1, so here we go. 1 equals minus 2 over 2 squared plus c over 2. So here we go. 1 equals, this is going to be minus 1/2 plus c over 2. I'm going to double everything because I can't be bothered. So 2 equals minus 1 plus c. So c is 3. Hooray! And that means our actual solution, our actual particular solution then, our particular solution is simply going to be y equals minus 2 over x squared plus 3 over x, like an absolute beast. We've crushed it. We're really good at this now. No trouble at all. Long video, I know, but we will finish it for, you get so much practice next time. I think it was worth doing the proof for the rest of this lesson and maybe 20 minutes more. Page 198, just question 3. If you want to do question 1 as well, that would be okay too. Question 1 only asks for the integrating factor though, so that's only the first step. Question 3 is the first one that I found that actually makes you solve. So yeah, I wouldn't do more than that. Keep it easy, okay? I want you in the pattern. Don't bother with the yellow and red today. There'll be a chance for yellow and red next lesson. Whew! Right, buddies, that's it from me. See you next time. Bye, buddies!